I'm going to start with the free body diagram for the sled. I'll represent that as a box. There is a force to the right that we don't really know how big that is. That's actually the problem. I'll just call that FA for applied force. And there is friction to the left, which we know is 200 newtons. And I know that my applied force to the right should be longer than my frictional force because I know it accelerates to the right. So I'm just going to erase a little bit of the length of that frictional force just to make it clear that the net force is to the right. And there should be some gravity and normal force, which are going to cancel out because there's not going to be any vertical motion here. Okay, so there's my free body diagram. And the main reason for drawing that is to hopefully more easily be able to figure out what's going to be happening for the net force here. So I'll write a statement for the net force, the magnitude of it. So what's the size of my net force going to be? Well, it's simply going to be the length of the right arrow minus the length of the left arrow. They're just in opposite directions there, so we'll just subtract. Okay, we're supposed to figure out this applied force here. So I can rearrange it, and that would be just adding the force of friction to both sides. So it's going to be the applied force equals the net force plus the force of friction. And you may try to go through the normal steps of using Newton's second law and replacing the net force with MA. The frictional force, we know the value is 200, so I'm not really worrying too much about that. For MA, the mass is given. It's given as 30 kilograms. I'll write that in the box here. So I'm not worried about the M. But what about the A? What about the acceleration? So they don't really give that to us outright. So we've got to use some other means. We've got to use our kinematics to figure that out first. So this is going to be a multiple section solution here. So I'm going to highlight the values that are going to allow me to get the acceleration. And I'll just put a heading off to the side here to find the acceleration. And just do that work there. So it starts out at rest. I'll write v1 equals 0. It gets sped up to 4.0 meters per second to the right. And that occurs over a displacement of 12.0 meters to the right. And I'll get the acceleration. So I will go back to checking out the big 5 formulas for kinematics, and it's going to be the last one. That's the equation that involves them all. So I'm going to cross out this term that's 0 and isolate for acceleration. So I think all I need to do is divide by 2 and divide by displacement. Fill in the values. So that would be 16 over 24. That's 2/3. So 0.667 is what I'll go with. Um, Now it's supposed to round to 2 sig figs, but I kept the third one here just because this is not my final answer. I'm gonna plug this number into some other equation, so I kept an extra digit there. I'm gonna use that acceleration and plug it into there. Okay, so now I have all the values I need to finish this off. So we call this working memory to keep, like there's 2 separate parts here, and just to be able to keep both parts in your mind, thinking about them at the same time, without losing sight of the big picture. That's a working memory thing. All right, so the mass is 30. Acceleration I just got is, well, it's actually 2/3. Like that 0.667 came from 16/24, which is 2/3, which I'm gonna write instead because when you multiply that by 30, it's actually a nice integer. And then plus the force of friction is 200. Okay, so 30 times 2/3 is 20, plus 200 gives me 220 newtons. That's the magnitude of the applied force. The direction is to the right, so I may actually write one more statement here. The applied force as a vector is 220 newtons to the right. And the rounding is right, I believe, because this last step here is addition. In addition, we look at the decimal places. Both of those are 20 and 200 are both to the nearest whole number. So my answer will be to the nearest whole number.